All right, let's say we build a bunch of these 8-bit banks of registers and we're going to use them as memory. We're going to store a bunch of numbers. We have a 1-byte bus, 8 bits, which sends an 8-bit digit to all of the memory locations. We're going to call this the data bus because it is transmitting the data we want to store. Now it needs to be able to deliver the data to all of the memory banks, so it is connected to every single one of them. The problem is we have a series of numbers, so we want to store the first number in the first byte of memory, the second number in the second byte of memory, the third in the third byte, etc. We don't want to store, say, 256 copies of the first number in all 256 locations. What a waste. So the problem is, how do we turn on or off the memory banks so that only one of them actually stores the number coming down the bus? We do it using a second 8-bit bus, which we are going to call the address bus. And we're going to give a unique address to every single one of those memory locations. We will control the memory locations using a function called demultiplexing. Let's say we wanted to send our first number, our first byte of data, to the memory location with the decimal address of 1. This is actually fairly easy to demultiplex. A decimal address of 1 would be a high on the binary 1 line, and all the other lines would be 0. So let's put a whole series of OR gates across the upper 7 bits of the address and daisy chain them. We'll put a NOT gate off of the 1 bit and run that into the daisy chain as well. The last gate in the chain will be a NOR gate, which feeds into the clock of the memory bank. Watch what happens. If any of these upper 7 bits is high, these are all OR gates, it will send a high to the final NOR gate, which will then output a low, and thus our memory bank will not be turned on. If the first bit is low, then the NOT gate will invert that to a high, which triggers the final NOR gate to a low, turning off the memory bank. There is only one combination that will trigger a high on the output of the final NOR gate. If all of the upper 7 bits are low, then all of these OR gates output a low. If the first bit is high, then the NOT gate inverts it to a low. All of the inputs on our entire daisy chain of OR gates are low. The inputs on the final NOR gate are low, so the output will go high, setting the clock line on the memory bank high, and that memory bank will then record whatever is coming down the data bus. We call this process demultiplexing, which is often shown as demux for short. Let's look at another example real quick. Now I wanted to show you an example using the common standard 2-input gates to demultiplex. But remember, you can get logic gates that have multiple inputs, or you can even build a logic gate yourself using transistors and have as many inputs on it as you want. You can also demultiplex in a number of different ways using different gates. So if you happen to have a whole mess of AND gate chips, you could use those if you had to. So let's turn on the circuitry at hexadecimal address 1A. That's 0001, 1010 in binary. So we want a high on the output of our demultiplexer only when these 3 lines are high. So we use a 3-input AND gate, which, when those lines go high, boom, we get a high on the output of the AND gate. Oh, but check it out. Any binary number which happens to have those 3 lines high would also trigger the circuit. 255 would trigger the demultiplexer, for example. So we need to exclude all other numbers. What do we need to check? We need to check that all of the other lines are zeros. Now you can do that with a NOR gate. If any of those other lines go high, we will get a 0 on the output of our NOR gate. We can then combine the signal from the NOR gate with the signal from the AND gate. So as long as both gates are outputting a 1, the final AND gate will also output a 1, triggering our target circuit. Let's say you had access to several NOT gate chips and AND gate chips. Another way you could do this is to slap a NOT gate, an inverter, on every line that needs to be a 0 and daisy chain everything through AND gates. This way, any zeros will be inverted to 1s, ultimately triggering a 1 on the output. Any highs on any of the other lines gets inverted to 0s, and the final AND gate never gets triggered. This whole process of demultiplexing and addressing happens a lot. usually in behind the scenes, as you'll see. But it's important to understand what's going on and how to do it, because occasionally you might need to do some external addressing. For example, later on when we use microprocessors, you might add some external memory of some kind, and you'll need to know how to address that memory. The main point being, you want to activate something by a specific number on a bus, and you do it with logic gates. So practice your newfound skill with some sample addresses and design some demultiplexing arrays for the following hexadecimal addresses. 11 AF FF 35. Now remember, your demultiplexer should only output a high when that specific number is seen on the address bus. So just hash it out on paper, and unfortunately this is a mind exercise. You'll have to check your own work for the simple reason that there is several correct ways of building a demultiplexer in each instance. Though feel free to post your circuit drawing in the comments, and others or myself can give you feedback to see if it works.